Welcome to a talk about worms in Vulkan. My name is Timothy Lattis, and this is the Neo Kino Graphics channel. Remember, the best kind of work is the work that you don't do. This talk is about becoming an expert in no-op style programming. Let's start with a little history. Vulkan is roughly a decade in at this point. I've been using worms in Vulkan since the beginning. It's how I do my engines. I've seen a lot of code bases and traces in my professional career. They're all quite complex and inefficient in comparison. I'm still hoping to teach others a better way. While I'm a compute-only engineer, modern frames could transition from graphics after raster laydown to compute, at which point these ideas could apply. Yeah, modern graphics. Tracking management hell. Are you sick of high-frequency overheads? Do we really need to do this? Is the graphics really going to taste better this way? Let's go into a side story. Once upon a time at AMD, around the time of GCN, early AMD compilers used GLC equals 0 for stores. That would leave fully written cache lines on incoherent caches. I convinced them to move to GLC 1 for all stores. That way you don't leave any of the fully written lines in the incoherent caches. You get less possibility of stale lines. It enables a lot more driver-side barrier removal too. I prototyped a driver with app-detect barrier removal. With some of the traces I was getting 10% whole frame perf returns. That's a lot. Note, doing work can also act as an implicit cache flush. So sometimes the unsafe barrier shouldn't work, but it does work because the work itself is actually flushing the cache. If you're reading through a lot of a linear block of memory that is an integer multiple of the cache size, the cache is likely effectively getting flushed possibly many times in that workload. So why am I putting a worm in Vulkan? Well, worm is really a memory usage model for optimal GPU compute. It limits the cache flush operations to once per frame. It minimizes the cost of the cache flush. It avoids heavy possible write-back in case a cache flush isn't pipelined by the driver. Mid-frame thus only needs pipeline events, no barriers. It removes the need for any resource usage tracking, no CPU overhead or complexity. All the associated bugs, work, and time and frustration just go away. Let's look at example cache levels on AMD RDNA. You have the I caches. Those are instruction caches, non-coherent, read-only. You have the L0. This is a vector memory. It's non-coherent but read-write. You have the K cache, or the scalar memory cache. This one's non-coherent, and it's typically read-only. You have the L1, potentially. Some chips, like RDNA4, do away with L1, turn it into a buffer. This is non-coherent and read-only if it exists. You have the L2, it's coherent. You have the L3, also coherent. L3 is known as the mall, the last level cache, or the infinity cache, depending on who you talk to. Note cache line size can be different for different caches. Next, let's talk about a Vulkan feature called layout memory qualifiers. In Vulkan, the GPU memory instruction cache control is provided by the layout memory qualifier. One can alias layouts on the same binding point to get different cache control behavior. So you would have layout, your set, your binding, followed by your memory qualifiers, followed by uniform, and then the name. There's three memory qualifiers we should dive into. The first is coherent. Use this for atomics. Coherent bypasses the non-coherent caches. Read-only. This is what we use for textures or to potentially get access to the constant cache. And then there's write-only coherent. All writes with worm are going to use this. Let's talk about cache flushes. There's two components. We got write-back. Write-back writes dirty lines back to the next higher cache or memory level. Worm always writes through to the coherent cache domain at the point of the store. The second component of a cache flush is the invalidation, the marking of the lines as invalid. Now let's go back and look what write-only coherent means, that memory qualifier, in the two kinds of caches. In the non-coherent cache, it means leave no stale lines. Writes could possibly use the non-coherent cache for write combining to collect all writes, say, from all lanes of a wave. Or if the hardware is really advanced, it could collect across a full texture clause. But afterwards, the writes write through to the next cache level, and the associated lines in the non-coherent caches are invalidated. Write-only coherent to the coherent domain is just going to do the write. So what does WORM actually mean? Or what does it stand for? It stands for write once, read many. Basically a simple set of rules. I'll give you a timeline. At the frame or submit boundary, there's an implicit cache flush. This is Vulkan behavior, or Vulkan driver behavior. All the non-coherent lines are going to be invalid at that point. Afterwards, for any given block or collection of lines, we're going to follow some basic rules. First, we're going to write once per frame. We can do any amount of atomics or any amount of coherent writes. And since we're doing write-only coherent, this will not leave any data in any of the non-coherent caches. After we're done writing, at some point later we're going to transition, say via vkEvent, to the point where we read as many times as we want. After this point, no more writes are allowed for that block, but any number of readers are allowed. So what is a block? A block is a collection of lines. Note, not all caches have the same line size. You want to size your block to support the desired feature portability. Likely a block should at least be compatible with the compression tile too. Let's start with some examples. AMD constant cache is typically 64 bytes per line. AMD's vector L0 cache can be 128 bytes per line. You can imagine a wave 32 is storing 4 bytes per lane, and they could do that every clock. AMD's DCC, for instance, for compression, it can be 256 bytes per tile, aka an 8x8, 4 byte per pixel tile. So something like a 1024 byte per block, that has a huge forward compatibility. So what about WORM and memory aliasing? What are the rules? It's okay to alias memory to change format or type between the write and the read transition. It's also okay to alias memory for, say, per frame dynamic resolution. Basically, any aliasing without per frame reuse is going to be fine. What I mean by reuse is meaning you're going to transition from write to read more than once. Aliasing with per frame reuse requires an extra mid-frame cache flush, so I don't use it. What about some bypassers? Hardware that breaks the rules. What about indirect dispatch? There are some old hardware that fetched indirect dispatch from the DRAM instead of the coherent cache domain. I have some simple solutions for that hardware. Either don't use indirect dispatch or don't support the older hardware. Both of those work perfectly good. Newer hardware fetches from the coherent cache domain, so having stores go to this coherent cache domain solves the problem. I don't even have to use indirect command buffer read transitions. What about Scanout? Scanout could either be fetched from the coherent cache domain, or alternatively it could be fetched directly from DRAM. Depends on the GPU architecture. Drivers in theory should allocate swap images as uncached if it's going to be fetching from DRAM. That way the image stores will just write out to DRAM, you don't have to do any later cache flush. However, there's no guarantee a driver is going to do that, so you may need the image transition for Scanout if the driver hardware does something stupid. I do a lot of front buffer rendering, which means you can't really transition. So now if we combine this WORM with the bind everything once idea, we get something that's extremely simple for GPU programming. In fact, at the beginning of the command, you're going to bind everything. You're going to do your dispatches. If you want to keep your dispatches pipelined, you use events, vkEvents. Basically, do a signal, then do some independent work, then wait on the signal, and follow that, and pipeline. What about submit and frame level effects? Well, first thing you should do is go read this article, GPU Submission Strategies, that AMD published. It's fantastic. What happens at command buffer boundaries? Well, they have guaranteed depipelining on AMD. Even if the driver chains command buffers in one submit, yeah, it depipelines them. So are we done here? Possibly. Let's start with some basic rules for maximum perf. These are hard rules. You violate the rules, you definitely run slow. First rule, only one command buffer per frame. Don't use multi-threaded record. I thought multi-threaded record was the whole point of Vulkan and DX12. Yeah, that's a paradox, isn't it? But no, definitely don't use multi-threaded record. Next thing, only submit once per frame. If you do this, you're limited to one depipelining event per frame. You cannot do better than that if the driver is going to wait for idle in its pre or post amble of a command buffer. Oh, but wait, I'm not dead yet. Wait, yeah, you are. Forget immediate mode. That's an IHV stick measuring contest. It's not really useful if you want good animation. Forget VRR. That can never be jitter free. That leaves VSync, guaranteed jitter free animation. And there's really only two options with VSync. Either you're hitting, good, or you're missing, total crap. This frame will always have an idle padding, a depipelining event, and that idle is going to be proportional to the expected frame time volatility. But we can rise from the dead, but not for this talk. Outside of Vulkan, it would be possible to do pipelining of frames, but one would need a workload that dynamically adapts to the cost of the frame. That's a little bit too long for this presentation. So what's the major takeaway here? Well, the dead simple approach can be both the fastest and easiest to implement and give you the best performance. Frees up some time to go hiking.